Welcome back. For those of you who have met before, welcome back. There have a couple of new students in class that I haven't met before, so welcome. And I hope you don't get COVID. I already have like 5 students sending me emails that they got COVID and they had to stay home. That's why we record all of the lectures and I post them on YouTube. If you were part of the Lab 1 class, you should be somewhat familiar with the YouTube structure. I posted some of the lectures, not all of them. But Lab 1 doesn't really need that much of a lecture, right? So all of the lectures are going to be posted on YouTube, but your attendance is required. What does that mean? It essentially means that you have to submit the quizzes that I give you in class. If you don't want to come to class, that's all right. Just watch the YouTube lectures online and send me an email with a PDF, like response with a PDF of the quiz, your answer to the quiz. Does this make sense? Okay. But keep in mind, the YouTube lecture, the online lectures are not a promised part of the lecture. So they usually are very behind, right? Because this is not an official part of the lecture. This is just, I just do it to help you guys. So keep that in mind. So with that aside, let's just go ahead and go over the syllabus. All of you should have a hard copy of the syllabus. If you don't, there is some more here. This is the flight and orbital mechanics. Yeah, make sure to take the syllabus. It is a very interesting course. I really like the course myself. And of course has 2 parts, flight mechanics and orbital mechanics. And this is the only course in which you will get some exposure to space. Spaces. Like half of the class is orbital mechanics, so you will see a lot of space-related stuff for half of the class. You should be very well-versed in mathematics. This is a very theoretical class. So you should be very well versed in mathematics, also in dynamics. This is essentially a continuation of your dynamics. It will get some parts of it are very far away from dynamics, but most of the theory is essentially advanced dynamics, right? That's why we will do, for the first 2 lectures, we will do a small review of the dynamics you will need for the class. So make sure you understand statics, dynamics, and also calculus very well. If you don't, please reach out to me and we'll see what we can do to help you to essentially cover the basics. Okay? Any questions so far? You are, of course, welcome to ask the questions, any questions you may have during any lecture. You have my phone number listed here. That's my office number. And the office hours are Mondays from 11 a.m. to 1 p.m. If you want to come to my office, you can send an email. You can come anytime. Just send an email beforehand. I'm usually not in my office during the office hours if you don't send me an email and make an appointment beforehand. So I don't really mind you showing up anytime that I'm in the office, but I'm usually not in the office. So if I'm in the office, just knock on the door and come in. If I'm not, just send me an email and we set a time outside of the office hours. So these office hours are here just because they have to be here based on university policy, right? You can come to my office anytime. But just make sure, send me an email beforehand so I'm in the office. And my office is located here in this building, in Wing A, room 117. Room 117. Right. Textbook. We have 2 main textbooks for the course and 2 additional textbooks, I would say, that are not required for the course, but we are going to use them a little bit. The first one is actually the second book here, Elements of Airplane Performance. This is the book we are going to use to cover the flight mechanics part of the class. It is a very small book. The problem with this book is that it doesn't have any practice problems, right? that is why we also use the Introduction to Flight book by Anderson, which is a book I think you also use in your Aerospace 101. All right, but for our course, we are going to use chapter 6 and 7 and 8. So the theory is going to be based on elements of airplane performance, but the examples and problems and homework is going to be from Introduction to Flight, or some of the problems that I've designed myself, or I've borrowed from some other courses. And the orbital mechanics part of the class, we are going to mainly rely on orbital mechanics for engineering students, which I have right here. It's a very thick book. We won't be able to cover all of it though. Up to chapter 7. That is all we are going to be able to cover. Let's see. Yes, up to chapter 7. I'm hoping we can cover chapter 8 this semester as well, which is the interplanetary trajectories, but I don't think we're gonna have enough time. This course should be 2 separate courses. But since you guys take a lot of Carolina core courses and non-related courses, we don't really have the room for an additional course. That's why we have combined these 2 courses together. Class meets at Tuesdays and Thursdays, 10:05, 11:20. You're in a class, so I assume you already knew that. And in this location, you have the course topics here. For the flight mechanics, we are mainly focused on equations of motion. We are going to play with equations of motions to get the different types of flight, like landing, cruise, descent, all of those things. So we are going to start with a very general equations of motion for the 3-dimensional flight, and then we are going to simplify it step by step. And then for the orbital mechanics, we will talk about the orbital maneuvers, orbit determination, 2-body problems, the Kepler equations, Kepler laws, and all of those fun things. Any questions so far? No. Okay. Let's talk about the lecture. This table, this is a standard table that you should come with all of your courses. I mean, this is a university issue table. The topics part of the table in my classes are essentially something that I wish I can do, right? They are very, I would say, visual thing. It is, I don't think we can finish all of these topics in this semester. I wish we can, but things come up, problems arise, so I don't think we can really finish all of the topics in the topic section. But the assignment sections, we will get to all of them. There will be 11 homeworks, a lot of homework, but all of these so essentially you are going to have a homework each week. But these homeworks are going to have between 1 and 3 questions, right? And so they are going to be very short homework. I've broken down the 4 homeworks I gave in the previous lectures because I wanted to make sure that you are staying on topic. So each week we cover a lecture, then you get the homework, you have like 3 days to finalize the homework during your weekend, you submit it, and then we'll get to next week. They are going to be very short homeworks. We will have some programming, very little, with MATLAB. And I'm assuming you have already passed the numerical methods course in this university. I don't know, I know our numerical methods course is not a very serious course, but don't worry about it because our use of MATLAB is going to be very limited. And I'm going to give you an introduction to what we need, right? I'm pretty sure all of you can handle our use of MATLAB. There will be 2 exams, 2 midterm exams. One will be on the topic of flight mechanics and also the review of dynamics. It will be just before the spring break on Thursday, March the 3rd. And the second one is going to be April 14th. And then the final exam is going to be on May 3rd, on Tuesday at 9 a.m. For the final exam, you will have 2.5 hours to finish your final exam. For exam 1 and exam 2, you will only get 1 hour and 15 minutes. Okay. I don't mind extending the time, but since we are taking the exam in class, and there are classes after our class, I assume, I don't think we can extend the time for the midterm exams that much, so come prepared. There are a couple of you who have had my energy, power, and propulsion course. I don't know how you felt about that course. Hopefully it was easy. I see one person thought it was easy, which is good. And yeah, so if you have a question about how I give my exams, you can talk to your peers and ask them how the exams are gonna go. Is there any questions so far? Yes.
Are you gonna do like you did in that class where the final, if it's higher than one of your other grades, you're gonna put that or
Yes. So let me tell everyone in class what you meant. Zach was in my propulsion class. What we did for that class was I told the students, if you get a very good score on your final exam, I will replace one of your lowest midterm exam with your final grade, right? That was the deal, right? Make sure to get a syllabus. But yeah, we can do that this semester as well. I'm not really opposed to it. Any other questions about the exams, about the homework, about the course topic? Something you have to keep in mind is that I try to force my students to be engaged in class, right? So you will be asked questions. And if I ask a random question no one answers, I will go one by one and make everyone in class respond to answer that question, right? So be engaged in class. If you feel sleepy, you can just send me an email and tell me that I'm really sleepy, I can't come to class today. That's all right with me. But when you come to class, don't be sick, first of all. If you are sick, don't come to class. We can meet any other time. I will try to help you learn the material outside of the classroom in my office. And if you come to class, don't be sleepy, don't be tired. You won't get you will get the attendance point if you just send me an email beforehand. Any questions? No? Okay, that's good. Everything's clear. So let's go. Make sure to read this part of the syllabus, but these are very standard. There's nothing special about them. Late work is not accepted unless you have sent me an email and asked for permission, right? Which I usually give, right? If you send me an email and tell me that I had this exam, I couldn't work on it, I need 2 more days, that's all right with me. But you have to communicate with me. Communication is the key, right? Just make sure to talk to me. If you come to me at the end of the semester and tell me, yeah, I couldn't submit these many homeworks, that is not acceptable, right? You just have to talk to me throughout the semester. Okay, great. As I said, attendance is important. So 8% of your grade is your attendance. That will be determined by your quiz submission. Right? So I give out the random quizzes in the class. You just have to start working on them and submit the quiz to me. It doesn't need to have a correct answer. As long as your name is on the paper and you have tried solving the problem, you will get the point, right? It's just to make sure that you are engaged in class, you understand what's going on. Or if you don't understand, it is for me to understand that you need the help, right? Homework are going to be 2% each, so 22% total. Exam 1, 20%, exam 2, 20%, final is going to be 30%. There will be a lot of bonus points prepared throughout the lecture. You can earn up to 20% of bonus points. I think one person in my propulsion class actually had 15% of bonus point. Yeah, they didn't need it. He got an A, but had 15% of bonus point, which is going to bump your grade a lot, right? So make sure to work on the bonus point. And bonus points are generally very easy. So if I don't want to do a proof of a derivation, if I don't want to derive an equation in class, I tell you that go home and find the derivation, bring it to me, you'll get a bonus point. Bonus points are usually going towards 0.5%. half a percentage, essentially. So you can earn, like you can have 40 bonus points to get 20% of the total grade. Any questions? No? Okay. Grading, very standard. 90 is going to be an A. 85 up to 89.99 is going to be a B plus. So if you feel like that you are going to get 89.99, make sure to do a bonus point, submit a bonus point, then you won't need to send me an email and ask me to bump up your grade. Okay. And yeah, attendance policy, we talked about the attendance policy and the diversity and the integrity part. Yeah, any questions? No question. Okay, so I usually go through the introduction every semester. Let's go through the student introduction this semester as well. There are a lot of you in class, but hopefully we'll go through this as fast as possible. I know like half of you by name, and I know like 80% by their face, but I don't know everyone by their name. And there are a couple of you who are new. So let's just start from there. It's behind you.
My name is Jason Garrison.
Introduce yourself and like say whatever you want about yourself, your hobbies or whatever. Research hobbies, like if you are a gamer, what do you play?
Junior aerospace, obviously. Minor in astronomy. I don't know. That's pretty much it.
Okay. Jason, minor in astronomy. Okay.
My name is Maddie Roberts, and I'm excited to have a 3-day weekend every week.
Okay.
My name is Robert Demuth. Majoring in aerospace, obviously, minor in nuclear engineering, and I enjoy outdoor activities like hiking, kayaking, camping.
I'm West, junior aerospace, as with everyone. I'm excited for the baseball season to start up.
Okay. So,
Maximus, or Max, sophomore, aerospace engineering, obviously. And I do play games, big, like, adventure, RPG kind of person. Big sports fan, and I guess that's about it.
okay.
My name's Drew. I'll skip the commonality. I rock climb, mountain bike, and work with robots.
I'm Sam.
What was your name again?
I'm Sam.
Sam.
I work at McNair, and that's all I can tell you.
Okay. That's fair.
Patrick Murphy, recently got a puppy.
Good for you.
My name's David Doe.
Just have to speak up.
Sorry.
That's all right. David. David.
My name is Kerem. I'm Turkish aerospace engineer again, and I like motorsports.
More. Cool.
I'm Kevin Brown. Play hockey, play video games, play D&D.
Okay.
I'm Patrick Bailey. I play video games and I do research in additive manufacturing.
I'm Horton Gibson, and I'm a big fan of video games, and especially Legos, and I make a whole bunch of stuff. But we'd be here all day if I try to tell you everything I made.
Alright, I'm Jacob. Play a little bit of video games. Looking forward to Elden Ring when it comes out later this year.
I'm Jack Hill. I'm a junior. I like to rock climb and do some other outdoor activities.
I'm Jessica Fisher. I'm excited for some new games to come out this year. I do concept art.
I just gave games as an example. You don't all have to play games. You can do whatever you want to do.
My name is Zach, and I like to do basically anything outdoors. Hunting, fishing.
Good.
My name is Kevin Zimovan. I'm majoring in mechanical engineering, and I do research at McNair, and I like to longboard.
We have the lone mechanical engineer. Make sure to make him feel welcome. Yeah.
My name's Chris.
Yeah, sorry.
I'm a mechanical engineer.
Oh, you're a mechanical engineer as well. Okay.
Play golf.
Okay. Two mechanical engineers.
I'm Melissa. I like to read and travel and anything outdoors.
Good.
I'm Bryson. I like to work on my car and I also like to work on vintage electronics.
I'm Hunter. I enjoy flying and weightlifting.
My name is Shruti. I'm a sophomore doing aerospace engineering, minoring in computer science. I like to play badminton, travel, cook, literally everything.
Okay.
My name is Jordan. I like playing games, like going outside, going on hikes and stuff.
Okay.
My name's Matt. I like sports, early fishing, and just anything outdoors.
Cool.
My name is Jackson. Aerospace engineering. I'm excited for school, which is weird. And I'm also excited to start my research project this semester on heat transfer.
Who are you working with?
Dr. Lee.
Chen Lee.
He's in the mechanical engineering department.
Okay, cool. It is not weird, by the way. That's how it should be, right? You are students here, you should be excited about school. And you're paying for this, so you should be excited. Yes.
My name is Tristan Guerin. I'm a junior aerospace engineering student. I enjoy video games, Legos, and sailing.
Why are you sitting at the back this semester? You used to sit up front.
Got here late.
Oh, okay.
I also got here late. My name is Danny. I'm a junior aerospace, and I enjoy golf, baseball, and math.
Golf, baseball, and math.
Yeah.
Nice.
My name's Ross. I'm a senior mechanical engineering major.
3 mechanical engineering, okay.
We're actually all in the same senior design class, so we're like, let's take this elective.
Okay.
But I like wildlife photography,
Nice.
anything outdoors, surfing.
Okay, cool.
I'm Justin. I like outdoor things, skateboarding, just playing kind of any sports and just enjoying the sunshine and stuff.
Okay, thank you. So except for those of you who are mechanical engineers, the rest of you are gonna see me for at least 2 or 3 more classes, and we are going to do this again and again, so yeah, be prepared for it next semester. Even mechanical engineers, you may take an aerodynamic course next year, the graduate level, so we'll see how it goes. And so the introduction is done. Let me ask you this question. I want you to tell me, what do you expect out of this course? I don't want to start the heavy part of the class today, especially that the first part is the review of dynamics. I'm pretty sure no one really likes dynamics that much. It is a very complicated topic. It can get very complicated. So I want to postpone the dynamic part of the class as much as possible. So let's do this. What do you expect to learn out of the class? What do you expect? Let me break down the question. Most of you know me as your instructor for the lab. Some of you know me as your instructor for the propulsion course. And maybe some of you don't know me at all, which is fine. You will get to know me. So my question is, what do you expect from me as your instructor? What do you expect from the class? Give me a second. He has a lot of things to say. That's all right.
Better than my aerospace 101 professor, and we're all good.
Who was your aerospace 101?
Van Horn.
Well, and half the time, Jesse.
He just played random videos every class.
Okay. So you don't want me to play videos. That's all right.
A solid foundation.
A solid foundation. Okay. Let's just make it a little more organized, right? So the first question is, what do you expect from me as your instructor? What do you expect to learn from this course? And anything else you want to talk about, I'm open to hearing. Just give me 1 second. Just give me 1 second to finish this. So as you know, I'm also involved with the ABET accreditation of the program, which is going to start soon, the process. So if you want to talk, if you have anything to say about that part, the accreditation or the general overview of the program, I'm also open to hearing that as well. Justin, right?
Mm-hmm. I was just gonna say that I'm excited to learn about space a little bit. This is the first kind of space focused course.
It is this space part is exciting to me as well. I really enjoy teaching, but it is very mathematical. So you just have to try to be try to understand. Go ahead.
I mean,
Max, right?
yes. I mean, I just expect you to like be interested in what you're talking about at all, because I feel like that's probably the best way to teach is like if you actually care about it, I understand it more.
Okay.
But also just like working with any students that are like struggling with it.
That's fair, and that's what I try to do, yeah, of course. Sure. That is a very fair expectation. Anyone else?
I want to learn orbital mechanics so I can be a professional by the time Kerbal Space Program 2 comes out.
Oh, yeah.
Yeah, that's the goal. You are here to learn a little bit of orbital mechanics, at least the fundamental parts. Then hopefully we'll be able to build up on it. Yeah.
I'm excited to learn about like maneuvers and how they like could affect like how like items fly through like projectiles and everything.
Hopefully we'll get there. I mean, if we move fast enough, we will be able to cover the orbital maneuvers. That's my goal. So, anyone else? We have 36 students. I mean, we have 36 students registered. I think we have 30 students in class today. Just 5 comments. It's not enough. Yes.
I really hope that we can get to everything, like cover every topic that you want to cover.
Yeah, me too. That's a very fair expectation. The thing is, the problem with going fast is that we won't be able to solve that many examples. There's always a balance, right? And I'm always accused of not solving enough examples. So I have to, yes.
I hope that the things that we...
I knew you wanted to say something about this, yeah.
I hope that what we learn will actually be able to be used in the industry and won't just kind of fall by the wayside.
Okay, so let me put it this way. This is a very theory-heavy course, and it really depends on the industry you'll end up in. I don't think most of you won't use these theories, at least directly in your day job. Maybe the understanding and perspective, yes, but the equations, I don't think you're going to use in your day job. I mean, if you work in NASA, yeah, definitely, or Boeing maybe, the flight mechanics part of Boeing, yeah, not the structural part. So it really depends on the job you'll end up in, and keep in mind this is a very theory-heavy course. Yeah.
I want to say that I have a question too.
Sure.
I just hope it's kind of like a propulsion class where back and forth, we were about the topic, but it was a very class, the talks we had about
Yeah.
it, so that you get a little bit more out of it.
Yeah.
Did that guy that ever get hired, that we went and watched, because you said that he was going to...
No, that guy didn't get hired. So yeah, my goal is to always keep the class an interactive class, so we interact with each other, yes.
How hard is this going to be for a mechanical major with no aerospace?
Impossible. Can't happen.
I mean, no, it's not gonna be. I mean, it really depends. I don't know your background, but you're a junior, right?
I'm a senior.
Senior. Oh yeah, all of you are seniors, right? And I assume you have a good understanding of dynamics, fluid mechanics, right? It shouldn't be that. It is definitely harder for you compared to the rest of the class, but it is not going to be that hard. It is manageable. What other courses do you have this semester?
Aerodynamics.
Is it with me again?
Yeah, it is.
Okay. Cool. Yeah, okay. Yeah, give it 2 weeks.
Okay.
Let's see where it goes. So all 3 of you have aerodynamics as well?
I do, yeah.
Okay. Okay. Yeah. That's aerodynamics. So if you are taking aerodynamics and this course, I think you should be fine. Because whatever you don't know here, whatever background you don't have here, we are going to cover over there. Okay. Anything else? No? None? Okay. Let's go ahead and start the class. I prepare PowerPoints for each lecture, but I don't use the PowerPoints. I try to use my tablets, but I will upload the PowerPoints for your use. So that's the goal. So I mean, sometimes I may miss the PowerPoints But that's it. And I I forgot to upload the PowerPoints on Blackboard for this lecture. But from the next lectures, hopefully you will get the PowerPoints on Blackboard before the lecture. So if you want, you can print them out and bring them to class, and then like write your notes on those PowerPoints, right? That's why I usually I bring the PowerPoint with me just to remember what I want to teach. Okay, and also the recordings of the class are. My plan is to post all of the recordings the next day, right? But sometimes things get mixed, right? So let's go ahead. Flight and orbital mechanics. The first part of the class is from your orbital mechanics books, the chapter 1 of the orbital mechanics. I think I have to make this smaller. Orbital mechanics for engineering students. And this is it is called the dynamics of point masses, which essentially means that we are going to. What does this mean? Let me ask you this. Let's make this the first question. Let me ask Zach, who was very interested in the interactions, and I appreciate it. What does a point mass mean? Yes, let's go.
It's not a rigid body, so it's not going to have any length like moment of inertia or anything like that.
Exactly. So that's a conclusion you make from this. So essentially, it means that it is not going to have any dimensions, right? It is a point with a mass, right? It doesn't have any x, y, and z dimension. It doesn't have any volume, right? It is a point. So we are going to start the review by the dynamics of point masses, and we are going to, for most of the lecture, we are going to assume that a plane is a point mass because a plane is much smaller than the Earth, right? All right. For the flight mechanics part of it. And for the rest of it, for the orbital mechanics, we are going to start by the assumption of point masses for each, I guess, the orbital objects or the planets or lunar trajectories. And then we are going to move on to rigid body assumptions, which will happen hopefully later, right? Okay. But the first thing we always start when we are talking about dynamics of point masses or any mathematical analysis here is by the introduction of vectors. What are vectors?
A magnitude with direction.
Exactly. So in vector, we are going to have a magnitude and a direction. The direction part is what that is the thing that separates vectors from scalars, right? And we are mostly dealing with scalars. If any part of this review felt new to you, so meaning that if you haven't learned this before in your dynamics course, let me know. I will stop and try to explain it a little more. If you don't tell me you don't know something, I won't know you don't know it, right? Just have to tell me that I haven't learned this before. Okay, so essentially what this means that if a vector is pointing, if two vectors have the same magnitude and are pointing in the same direction, they are the same vectors, right? Because the only thing we use to distinguish vectors from each other is their magnitude and their direction, right? Their placement in a space is trivial, it's not important, okay? So these two vectors. And one thing we define here is a unit vector. The first thing we define after the introduction of vectors. What is a unit vector? A unit vector is a vector which magnitude is 1 is unit, exactly. And we can define a unit vector for any vector, right? Let's say you have a vector A, and we want to find its unit vector. You essentially have to divide that vector A by its magnitude, right? In Cartesian coordinate system, it is going to look like this. And this course, we are mostly going to deal with Cartesian coordinate system, which I assume is good news to everyone in the class. We are not going to use cylindrical and spherical coordinate systems that much. Right? We are going to mostly focus on Cartesian coordinate systems. The normal mathematical operations apply to vectors. We can add the two vectors together. We can subtract two vectors. We can also multiply the two vectors. The multiplication part is the part that is different. There's a little difference when it comes to, when it comes to vectors compared to a scalar multiplication. For the summation, A plus B is equals to B plus A. That is the summation rule in vectors, which is also true for scalars, right? It essentially means that you have to add all of the components of a vector with each other. Let's say you want to present this addition with their components. It's going to be AX plus BX I, AY plus BY J, and AZ plus BZ K, right? In Cartesian coordinate system. It doesn't really matter if you write B first or A first. So that's the summation rule. It has a very simple proof here. Any questions so far? So very simple topics. Simple object. The unit vector can also be calculated based on using the angle a vector makes with the coordinate system. So the angle it makes, this vector makes with the x direction is going to be the cosine of that angle. Is going to be the magnitude of the unit vector in the x direction. Let's say this is vector A, and we have x, y, and z here. The angle this vector makes with the cosine of that angle with the x-axis is going to be your unit vector component in the x direction. The angle it makes with the y-axis is going to be the cosine of the angle it makes with the y-axis is going to be the unit vector component in the y direction, and the angle it makes with the z direction, the cosine of that angle is going to be the unit vector component in the z direction. Why is that the case? Is there anyone who can tell me why that is the case? Unit vector has to be the same, right? With this definition and this definition. So why can we say that the cosine of those angles are essentially going to give us the unit vectors? Yes?
Is it just a Pythagorean theorem, so like cosine of that angle would equal to that vector divided by the x component of that vector divided by the hypotenuse, which would be the magnitude?
Exactly. So the cosine of this theta is going to be the projection of A on this axis, which is A of x divided by the magnitude of A. Okay? Same is true for the cosine of the other angles. I have to mention something here. Your book, in this orbital mechanics books, whenever they are talking about the vector, they use a bold font. So if you were to purchase the book, and if you wanted to read the book, whenever you saw a bold font, they are talking about a vector, right? Which for my case, I just use a vector sign, right? And whenever you see a non-bold sign, a regular font, that talks about the that is talking about the magnitude of a vector. Magnitude of a vector. Which I use as well. I use the magnitude sign as well as a regular just letter, right? Just make sure you are aware of this so you won't get confused. So we have talked about the summations. We have talked about the vectors in general, the unit vectors. The next thing we need to address here is the multiplications of vectors. For scalars, let's say you want to multiply 3 by 4, it is going to give you 12, right? Pretty simple. We have known this since primary school. We are very well versed in it. But for vectors, it is not the simples. It is not the simple. It doesn't work for vectors. Who can tell me what are the differences between vector multiplication and a scalar multiplication?
Like in vector multiplication, how it's stressed. You basically have to multiply the row and the column, but instead of that way, not how it's stressed. You have to multiply every term basically.
Okay.
Add them together to get that.
Okay.
Like you might start out with 3 by 3, but that's going to end up for 1 by 3.
Okay.
You get the same like size.
Okay, that's one part of it. Yes.
When multiplying the rows and columns, you have to make sure that the row part of one is the same as the column part of the other in order to actually have multiplication.
Exactly. So just one issue, we are talking about vector multiplications, not matrix multiplications, right? Just keep that in mind. Tristan, and then you.
I was going to say that in general, vector multiplication requires matrices.
Yes, that's part of it. Then you.
I was going to say, because when you're dealing with just normal scalar multiplication, there's only magnitude, and with vector multiplication, you have to account for the direction of it. So you have to count the x values and the y values and z values separately as if they're their own thing, unlike normal.
Okay, thank you.
The product of cross multiplying two vectors would be a vector that is normal to the two original vectors.
Okay, so based on whatever your friends, your peers mentioned, and all of these were true, we have essentially two different types of multiplications in vectors. One is called the dot product, and one is called the cross product. Right? I'm pretty sure you have heard the names and you should be familiar with it. But based on my experience, most people forget what is the difference between a dot product and a cross product, and what are those essentially. So we are going to talk about them a little bit. The dot product of two vectors, or the inner product, dot or inner product, is essentially going to give us a scalar, right? So the dot product, we can calculate the dot product by calculating the magnitude of both vectors, multiplying those, and then multiplying them by the cosine of the angle between the two vectors, right? That will give us the dot product, which essentially means that the dot product is a vector, let's say vector B, multiplied by the projection of the vector A cosine of theta, on vector B. So let's say you have vector A, vector B, theta. You project this vector A on this vector B, and then you just do a regular multiplication, right? As long as you use this formula, it should be fine. We can also do the dot product with their components. So the dot product of A and B is going to be ax multiplied by bx, and ax and bx are scalars. I'm sorry. Plus by ay plus az bz. So the dot product of two vector is going to give us a scalar. What is the dot product of two vectors that are perpendicular? 0, because of the cosine of theta, right? So based on this, what can you say about this dot product? I dot j is also 0 because they are perpendicular, right? What about I dot I? It is 1, right? We can also say this the exact same. We can make this exact same conclusion about the other unit vectors in the axis, like ij and k, all of them. So based on this, we can actually prove this. This is very simple. We have axi plus bx, axj, ayk multiplied bx. When you're dealing with vectors, a lot of components is going to get confusing. So byj and bzk, right? If you were to perform these multiplications like a scalar multiplication, how would you do it? Just multiply this by this part first, right? So it is going to ax bx I multiplied by I, so 1, right? Then multiply this by this part, ax by j multiplied by I, 0, right? Do this for the third one, ax bz I k, also 0. If you do it for ay and az, you would see that you will get I multiplied by k here, j multiplied by k here, j multiplied by j, and j multiplied by I, j multiplied by k. So 0, 0, and so on and so forth. And eventually, when you clean it up, you will get ax bx plus byay plus az bz. Pretty simple. That's why a dot product of a two vector is going to give us a scalar. Very simple proof. What about the other multiplication scheme? A cross B. This is essentially going to give us a vector. Let's say theta A B. That is perpendicular to both vectors. Okay, how do we calculate this? Since this is a vector, we have two different definitions for it. I mean, the two different definitions are going to be different. First is the magnitude of this vector can be calculated by multiplying the magnitude of vector A by magnitude of vector B multiplied by the sine of the two vectors. This is going to give you the magnitude of this vector. We can actually present this in a vector form as well. Just have to multiply by the normal unit vector that is normal to both A and B. So you have to find this normal vector that is both normal to A and B first, and then multiply it by this magnitude. You will eventually get the correct vector form. But there is an easier way to get the vector form of this cross product. Who can tell me what is this easier way? the determinant, there are a couple of methods. Yeah, the method I usually use, I didn't hear what you said, but I assume it was correct. The method I usually use is taking the determinant, right? In Cartesian coordinate system, we take the determinant of this matrix. Do we know how to take this determinant? Yes?
Yeah.
Okay. So we are not going to go over this. But let's talk about the unit vectors in each direction. What can you say about I cross I? It is going to be 0 because of this sign. So the theta, if the angle between the two vectors is 0, then the cross product of those two vectors is going to be 0, which essentially means that there is no vector that is there is no single vector that is perpendicular to both of them. And that makes a lot of sense. Let's say we have vector A and vector B. There will be millions of vectors that are infinite number of vectors that are perpendicular to both of them, right? Because there's a plane that is essentially perpendicular to two vectors that are in the same directions. There is no single vector, right? What about I cross J? It is going to be K, exactly. And J cross K is going to give us I, exactly. K cross I is going to give us J. Okay. So what can you say about J cross I? Is going to give you negative K, exactly. And if you write the determinant and do the calculations, you can actually prove this. It's not a very complicated proof, but this essentially leads us to conclude this very basic rule, that A cross B is equals to negative B cross A. And there are a couple of other cross product rules, dot and cross product rules that I'm just going to mention. A dot B cross C is equals to A cross B dot C. What is the result of this multiplication? It is going to be a scalar, exactly. And there's also a cross product expansion rule, which is called the back cab rule. It is called the back cab because it is BAC CAB, right? So the naming is to help you to remember the rule itself, right? So you can expand the cross product of three vectors to look like this. So on this side, we are going to see a vector. What are we going to see on this side? This is a dot product of three vectors. It should still be a vector, but is it? That's my question. So you are making the dot product here, which is
Scalar times a vector.
exactly. Thank you. So you are going to have a scalar in the parentheses, and the scalar multiplied by a vector. It's just a regular multiplication. Just multiply that scalar with each component of the vector. It is still going to give you a vector. Any questions so far? Okay. Let's move on to the review of kinematics. Just make sure you understand everything about the cross product, which I hope you do. You did already. And we are going to move to kinematics to just remind you of some kinematics problem. Let's say you have point P that is moving on a path, on a curvilinear path. What is it? You don't like curvilinear path? Why not?
Just at least the way it's taught too.
Okay. I'm sorry. So what is a curvilinear path? A path that has a curve.
Path that changes in more than one of the rectilinear, like more than one of the coordinates. So either can change in both x and y, or x, y, and z.
So a rectilinear path can also change in x, y, and z, right? So this path can be a rectilinear path, and it's changing in all directions, right?
I thought we usually measured them in theta, z, and like a radius to a center point.
Curvature, right?
Yeah.
You wanted to say something? No. That's all right. So yeah, so essentially a curvilinear path is a rectilinear path, is a straight line that has some sort of a curvature, right? I don't want to get into the technical definitions, just as long as you understand that this is a line, this is a straight line that has some curve in it, right? So let's say this point P is moving on this curvilinear path. And in kinematics, the analysis of kinematics is going to talk about the velocity, the acceleration, and also the position of this point, right? We are talking about the point masses, so we are only interested in this point specifically, right? How can we find the position, or how do we define the position of this point? Position of this point is defined by a vector r that is a function of time. So this vector r that goes from the center of the coordinate system to your particle is going to change with time. Essentially, your particle moves over time, so your position vector is also going to move with time, change with time. And this is a vector. This is a function of the x component, which is itself a function of time, the y component, which is itself a function of time, and the z component. Okay. How do we define the velocity for this specific particle? dr dt, which essentially is going to be dx of t dt, dy of t dt, and dz of t dt. We can also define acceleration. Acceleration can also be a function of time of this point P. This acceleration is just derivative of the x component of velocity with respect to time in the I direction, in the x direction, derivative of y component of velocity with respect to time in the y direction, and the derivative of z component of velocity with respect to time in the k direction. Okay, Something that you have to, I think I have to refresh your memory on, is that we usually show a time derivative with a dot on top of your vector. So r dot refers to the time derivative of r. And this is, whereas the a space derivative is shown with a prime, right? So if we were talking about r prime, we are talking about the r dr dx, right? We are mostly with time derivatives here, though. We are mostly concerned with time derivatives here. So your v is going to be r dot, a is going to be v dot, or r double dot. You can also say the same thing about the components. So this is one way of looking at the movement of this particle P. But we can also place the coordinate system on the particle itself instead of having a center. So let's say this is moving along a path. And our coordinate system, we can have a tangential normal vector as well as the tangential unit vector and a normal vector along this path. All right. Before moving forward, we just have to define the path. What is a path?
It's the direction of travel.
A direction of the travel. I mean, yeah, technically that's true, yeah. But it is defined as, path is defined as locus of points that particle P occupies in a space.
What's that first one?
Locus. Locus. So to be able to analyze our particle, and this type of analysis is actually very common, specifically in orbital mechanics. So just have to make sure you understand it completely. If, for those of you in mechanical engineering, I know, or I assume your instructors have talked about this type of analysis when they were defining acceleration for you, but I don't know if aerospace engineers have gone over this because you haven't taken fluid mechanics, right? So here, we just need to understand the tangential unit vector and the normal unit vector. And how are they related to velocity and acceleration, right? First of all, since your velocity particle is moving on this path, or let me ask you this. Let's say I want to define velocity. I want to find the components of velocity using this coordinate system. I want to sit on the particle and find the velocity vector based on this coordinate system, right? What would be the velocity vector? It will be in the direction of u tangent, right? Essentially. So our velocity vector will be only magnitude of velocity, or let's say magnitude of velocity in the tangential direction. So we can essentially define, that's u of t, not u of y. We can define this tangential unit vector as the velocity vector divided by the magnitude of velocity. Which essentially means that if you have this velocity vector in Cartesian coordinate system, you can find this tangential unit vector in the Cartesian coordinate system. So based on a different frame of reference, right? Does this make sense? Okay. What about acceleration? What can we say about acceleration? Is it the same as velocity? Or is it different? Yes.
The acceleration has two components, and one's along the tangential, one's along the normal.
Exactly. So acceleration can have the both components. It can be the tangential acceleration, and it can be the normal acceleration. This is actually A of t. What do we call the normal acceleration? So this is essentially, let's say this particle is moving the acceleration, right? This particle is accelerating normal to the path. Let's say this is a circular path. The particle is moving on it, and we have a force that is acting on this particle normal to the path.
Centrifugal force.
Centrifugal. It is centrifugal acceleration. Exactly, it's the same thing. And do you remember how we calculated the centrifugal or the normal? Let's call it the normal acceleration for this one. The normal acceleration. You have to speak up. I can't hear you. What I heard was correct. What was that again?
Tangential velocity divided by radius of curvature.
All velocity is tangential in this case, right? Because we are moving. So exactly, velocity, the magnitude of velocity. Thank you. The magnitude of velocity divided by the curvature, and curvature we use rho for. This is the Greek letter rho, which is also used for density. So make sure not to confuse the two. In the fluid mechanics part, we are going to use this symbol for density as well. Any questions so far?
It is velocity squared, isn't it?
It is velocity squared, yes.
What does rho equal again?
It's the curvature of this path. Let's say you are moving on this path. This rho is the distance at this specific location. Is the position vector from this to the center of this circle at this specific location. At this location, this distance can go here. The center of that circle can be here, right? That may be a different location. Does that make sense? The point is your curvature can change along your path, right? For a circular thing, your curvature is going to be 1 over r, right? 1 over the radius. I mean, it's going to be the radius. So your normal acceleration is going to be v squared divided by radius. We can also define the position vector of the curvature. Let's go to this path here. Let's say at this location, if you were to draw a circle that is tangent to the path at this specific location, not every part of this path, just that specific location we are at currently, right now, right? If you were to draw a circle that is tangent to that part of the path, you would be able to find the center of that circle, and I'm sorry guys, let's say this is your R, and this is the center of that circle. This position vector, which is called R C of P. So the position vector between the center of the curvature and the particle P, right? That is essentially going to identify your curvature. But the curvature itself, we are only going to use the magnitude of the value. So this vector is going to be rho, and it is in the direction of the normal to the path. So it's going to be rho un. Let me try to draw a better picture. This is the particle P. If we were to draw a circle that is tangent to only this part of the path, the center of that circle is going to be the center of your curvature, and that position vector is going to be named r c of p, and its value, its magnitude, is going to be equal to your curvature. And we can use the vector notation to show it. Calculating the curvature for an unknown path is a very difficult task, right? And you won't be calculating any curvatures, right? Because in orbital mechanics part of the class, we are going to assume that we are dealing with the spheres, right? As long as you have the radius, you should be able to calculate. You have the curvature, right? And just plug it in, calculate the normal acceleration if you have to. Does this make sense? Any questions? Have we seen this before? No? So some of you have seen it, some of you have not, but hopefully all of you are on board. So this, we can actually, there's one more definition that we want to talk about, and it is called the oscillating plane. Oscillating plane is a plane that passes through your path. And this plane actually can move with your path itself, right? So the oscillating plane is a plane that passes through your path at each location, at each time. And the unit vector for that oscillating plane is called a binormal. And if you look at this plane and the definition of the oscillating plane, you will see that this unit vector is perpendicular to the normal unit vector as well as the tangential unit vector, to both of them. So we can find this binormal by taking the cross product of the tangential and the normal unit vector. I think we don't have that much time left. Let me just introduce the concept of the distance traveled, and then we'll be done with today's class. Let's say you have this particle P that travels from here to here. That's P at time 0, P at time 1, right? And it makes this angle d phi, compared to the center of the coordinate system, of course. This arc length is called the distance traveled, or distance in general. And since this is an arc, we can calculate and since this is d phi, we are going to assume the position vector has not changed that much. So essentially, we are going to assume that position vector is the curvature here. So this ds, the arc length, or let me ask you this. How do we calculate an arc length?
Radius times the angle.
Angle, that's it. What is the radius here? Is the curvature, right, rho, and the angle is d phi. And ds dt is going to be the magnitude of velocity. So not the velocity vector, just the magnitude of velocity. You have to keep this in mind. Distance traveled is not a vector. Right? Which means that the phi dot, or the angle changes of this angle, is equals to magnitude of velocity divided by the curvature. Okay. Any questions?
That velocity, is that like average velocity over the distance s, or is it instantaneous?
So this is a very small change. This is a very like differential change, right? So we are assuming the velocity, velocity vector has not changed, right? Any questions? Okay, so that's it for today. 11:20 exactly. See you all